So first of all, just know that the schedule's been updated for our first exam, which will be the 4th of March, so not next Friday, but the following Friday on chapters 1 through 3. We'll be starting chapter 3 today, okay? Before we do that, I wanted to do another one of these review problems at the beginning here. No, I don't do that. This one revolving around those cyclohexanes and those chair flips. Okay, so this is the type of problem that we could see for this one. First of all, here's this molecule down at the bottom, this cyclohexane derivative. First thing we should be able to do is name it. Right, so give me the name of this particular molecule. Remember that we have this cis-trans stereochemistry with the names of our cyclohexanes. We can use this diagram below and fill in where those methyl groups should be on that chair flip diagram. Do that for both sides, and we can use it to establish which conformation is going to be the most stable of the two. Okay? So take a second to identify, first give me the name of this compound. And then we want to work on using this diagram here. This diagram is on Canvas. This is what you'll see on your exam that you're going to physically fill in. The methyl group goes here, the methyl group goes there, etc. All right? And so you can use this diagram here to evaluate which one of these two conformations is going to be the more stable one. All right, so I'll give you guys a second to copy it down, and then we'll go through it. All right, so first of all, the IUPAC name. Remember when we have these ring structures, we consider the ring to be the parent chain. So my parent chain is the cyclohexane. And then I got these two substituents on there. What are these substituents? How would I name them? They're methyl, yep. And then there's two of them, so what prefix am I going to have to stick out front? Dimethyl. I got to indicate the position of these two methyl groups. All right, so what would be my numbers that I have out front?
1 and 4.
1 and 4. All right, so 1, 2, 3, 4. Somebody had a question before about do you number clockwise, counterclockwise, whatever? It's always to minimize that number. In this case, it wouldn't matter if I had gone clockwise or counterclockwise. They would have both been at positions 1 and 4. But if I had something like this, for example, I would want to make sure to make that 1 and that 2, right? So it's just all about having the smallest possible numbers that you can. All right, and then the last thing was that we had to worry about the stereochemistry, right? Remember these wedge bonds. What does that mean when it's the wedge? That means that it's pointing out at you, pointing out of the page towards you. The dashed bonds are the opposite. They're pointing into the page, pointing away from you, right? So these two methyl groups are pointed in opposite directions. And so that would be, what do we call that? Oh, whoops. With our cis-trans stereochemistry, which one means the opposite sides? That would be trans. So the full name here would be trans 1,4-dimethyl cyclohexane. Okay, so then I'm going to go in and fill in this diagram here with these methyl groups, right? So I can tell what position that they're in. Again, the wedge means that it's pointed at you. The dash means that it's pointed into the page. So that's how I'm going to sort of interpret where to put these methyl groups on my chair structure here. On this same document, I made like this kind of like cheat sheet page here. People were saying that they were having trouble visualizing which one was the wedge bond and which one was the dash bond. So this isn't one that you're going to have on the exam, but just to sort of make sense of these diagrams here. Again, the wedge ones are the ones pointed out. So those are always, so if we look at a carbon, the wedge is always the bond on the top, right? It's not as simple as to say the wedge is always equatorial or the dash is always axial or something like that. It doesn't work like that, okay? So for example, if I move to carbon 2, the bond on top, the wedge is in a different position, right? But at each carbon, the wedge is the one pointing up, and the dash is the one below. Okay, so that's how I know to fill in. So let's actually, we can use this one for now just to make sure that we all see it. If I have my structure, this first carbon was the wedge. So that means that the methyl group would go on the top over here. And on this fourth carbon, the methyl group was at a dash bond. So that would be this position here. Okay? And then I'm going to do it before and after the flip. So I'm going to go after the flip. I'm going to again find carbon 1, put that methyl group on the wedge bond. Again, I'm going to find carbon 4 and put the methyl group on the dash bond. Okay, so if I look at these two structures, A and B, which one is the more stable conformation? Why B?
Both sides are in the equatorial.
Exactly, both of them are in the equatorial position. Remember, these big groups, they don't like to be in the axial position. So the more stable conformation will be B, and so the position of those two groups are both equatorial. Okay? These are the practice problems on OWL where it would have given you this cyclohexane structure and then asked, are these bonds in the axial or equatorial position? Okay? So this is the process that you would go through in order to solve those problems. There were only 2 options, and they give you 2 tries, right? So it wasn't that hard to kind of guess and check for those particular problems. But if you're really understanding what you're doing, it's going through this process, putting them in these positions here. So that's what I want you to do, is using this diagram, this document's on Canvas. You're going to take this, fill in the bonds with where those methyl groups should be, or whatever it was, an ethyl group, whatever it may be, and then figure out which one of these 2 conformations is the most stable, right? Using this diagram here is kind of the correct way to be answering those problems. Okay, so that's what I want you guys to sort of practice, and that's why I put that document there. So again, using this here, I would see that carbon 1, again, it's the top bond because it's the wedge. And on carbon 4, it's the bottom bond because it's the dash. Show after the flip as well. Again, these 2 are in the equatorial position, so this one is the more stable conformation. Okay? All right. So, closing out this sort of closed out chapter 2 with our reactions of alkanes. There is another practice problem that from what we did at the very beginning of class last time on the board here, just with a different molecule, starting out with now butane. The example we did last class was like 2-methylbutane or something, so it's a very similar example that's worked out where you got to figure out what the major product is. But yes, that's another sort of type of question that you can expect. Okay. So now we got to start in on chapter 3 here. The title of chapter 3 is Alkenes and Alkynes. Okay. What was chapter 2 all about? What was our functional group there? Alkenes. All right. So now look at our, if we pay close attention to our ending here, these are alkenes. And then the second type of functional group we're going to talk about are alkynes. So I'm changing that ane ending here. What was the type of bonds that we saw in our alkanes? They all had only one type of bond in there. All of them were single bonds, right? That's what made an alkane. An alkane was all single bonds. Okay, alkenes, now we're going to introduce hydrocarbons with double bonds. And alkynes are hydrocarbons with triple bonds. Oops. Right, so an alkane would have just been like all stick structures like this. An alkene is if there's a double bond anywhere in that molecule. Okay, so the presence of just one double bond automatically makes it an alkene. And triple bond, an alkyne has a triple bond in it. And actually with our triple bonds, we write them in straight lines like this. Let me actually get rid of these two back ones here. Okay, so this is a 4-carbon alkyne. Okay, we write them all in a line, and I'll talk about why that is here in a second when we talk about the geometry of these bonds. But nonetheless, also one of the harder things to sort of understand about the alkynes, or easy to forget rather, is on either side of the triple bond are carbons. Right? Those 3 lines represent 2 carbons that are triple bonded to one another. So this molecule, if I wrote out this sort of full Lewis structure here, would look like this. All right, so this and this are the same thing. Okay, so that's our 2 new functional groups that we're going to learn about today, are alkynes and alkenes and alkynes. Before we'll sort of get to reactions and all that good stuff next class, the first thing what we're going to do is talk first about like the geometry of these bonds. So remember with our alkanes, we said that these carbons were all had what we called this tetrahedral shape, right? Alkanes, because they have all single bonds, that means that each carbon is bound to 4 different atoms. All right, and so those bonds are all arranged as far apart from one another in space as possible, and it turns out that the way to do that is this thing called a tetrahedral. Okay, so all of these bonds are pointed, in different directions, all as far apart as possible. And this is called a tetrahedral. When we talk about alkenes, they have an interesting geometry to them because of that double bond. It's called trigonal planar. Basically, if you look at any one of those carbons in this double bond, it's got 3 bonds arranged in a triangle, and all of them lie in the same plane. right? All of these atoms, you can draw sort of this plane through, and all those atoms are lying in that plane. So if we take any sort of a double bond structure here, make it big and ugly, each carbon has its 3 bonds all in a plane, right? And that's true for both sides of the double bond. So all 6 of these colored atoms here are sitting in the same plane. All right, and so that's kind of what's pictured here in a bunch of different representations. You can see like this is the ball and stick structure, this is this fat sort of sphere structure, and then this is showing the electron density. So the red means that there's a lot of electrons there, and we'll sort of see why it's got a lot of electron density here in the middle in a second. But just notice that these are flat, right? The geometry of these molecules, all 6 of those atoms about that double bond are in the same plane. And so these molecules, at least in the region where there's the double bond, they take this flat shape. Okay? Do you have a question? No? Alkynes have what we call a linear shape around their triple bond. So not only are these 4 atoms, so if we look at any triple bond here, all 4 of these atoms are positioned in a straight line. Okay? That's why when we draw the structures for them, we have to go put our bonds sticking straight out as opposed to something like that. This would be wrong. Right? Because all those atoms around, those 4 atoms that are around that triple bond are all in a straight line. Okay, and again, that's what we call a linear shape. Okay? There is like something fundamentally different about double and triple bonds than about single bonds. Okay? Single bonds are what we call sigma bonds. Right? And the orbitals, right, so kind of like rewind to general chemistry sort of stuff, electrons live in orbitals. These orbitals overlap in order to form bonds. Okay? So in a sigma bond, in a normal like alkane, all sigma bonds, the bonds between the 2 carbons, if you like pictured those orbitals, they'd be sticking out like exactly kind of where you would expect bonding electrons to be, between the 2 atoms, right? So a chemical bond, a single bond, those sigma bonds that are holding these 2 atoms together, the electron density is sitting in between those 2 atoms, right? That's where those electrons are living to hold that bond together. That's a normal old sigma bond. When you get to 2 or 3 bonds, a double bond or a triple bond, the first one, if we take, for example, this is just this molecule here. That first bond is still a regular old sigma bond. That electron density is sitting between those 2 atoms. The other one, though, is what we call a pi bond. And pi bonds have a completely different shape in terms of like the orbitals that are involved. They stick out above and below those sigma bonds. Okay, so they're actually sitting on either side, right? So the sigma bond is electrons that are sort of overlapping between these 2 atoms. Those next bonds, the orbitals that are overlapping, are sitting above and below that sigma bond. Okay? Because of it, these pi bonds are way more accessible. Those electrons are easier to get to. And so we're going to see that these functional groups are way more reactive as well. Right? The electrons that are in that second bond, again, what I pictured sort of here in green. Again, the first bond is just a regular old sigma bond. But the second bond is one of these special pi bonds where the electrons live above and below those atoms, right? And because of that, those electrons are much more accessible and these functional groups are much more reactive. Okay, remember that if we look at these, looking at this diagram here, all of these atoms, so 1, 2, 3, 4, 5, 6, they're all sitting in the same plane, right? That flat shape. And that means that the electrons are sticking up and below that flat shape, which is why if we go back to our diagram here, we saw that there was a lot of electron density sitting above and below that molecule, right? So again, bottom line is those electrons are much more easily accessible, and so they're going to be much more reactive functional groups. Okay. The next sort of like consequence of these pi bonds is the fact that, so let's just draw this here. If we have like an alkane, single bonds can rotate. All right? So we have a tendency to draw these molecules in this like really big stretched out form. But actually every single one of these bonds is sitting there rotating all the time. Right? Molecules are always moving. They're always dancing around. Right? Unless you're at 0 degrees Kelvin or something like that. If you have any amount of heat involved, these molecules are moving around. So actually this thing isn't just sitting static as this like, zigzaggy line. It's sitting there spinning around all of its single bonds, moving all the time. All those bonds are rotating. So if I could draw this same molecule like that. These are both butanes. I've just rotated about that one single bond. We have a tendency to like to look at it in this long, stretched out sort of way. That's like the default standard for writing it. But this is the exact same molecule here. All right, I didn't actually change anything about my connectivity of atoms or anything like that. All I did was draw it rotated about that single bond. Okay? When we go to alkenes, double bonds cannot rotate. Okay? So these two methyl groups are stuck on opposite sides of that double bond. It can't just like rotate and put them back on the same side like we just showed with our butane. With our butane, we said that those two were the same structure. Right? But doubled bonds cannot rotate. So if I drew this molecule here, these are different molecules. All right, double bonds can't rotate. So in the one, the methyl groups are on opposite sides and they're stuck there. On the other, the methyl groups are on the same side and they're stuck there. So these are a representation of two different molecules. When we were talking about cyclohexane, the example that we just did at the beginning, we had this cis and trans designation that we used. And we're going to have the same thing for our double bond, for our double bonds as well. So if those two functional groups are located on the same side, it's a cis conformation, cis stereochemistry. And if they're located on opposite sides, it's the trans stereochemistry. All right, and again, the whole shtick is like these two molecules are different molecules. You can see here they have different properties, like different boiling points, for example. All right, they don't behave the same. They both have two carbons that are double bonded together. There are chlorines on either one of those carbons, right? So in terms of like their formulas, they're the same. But because of this stereochemistry, because that double bond can't rotate, they're locked on different sides, and so they have different properties. Cool? All right, so let's just do some practice here. Okay, so at this point we haven't learned much, but we can, for these two examples here, we should be able to identify which atoms lie in the same plane, and two, are these alkenes cis or trans? Okay, so everybody take a second and see if you can't, for these two examples here, tell me which atoms lie in the same plane and whether the alkene that's pictured is cis or trans. All right, so as for which atoms lie in the same plane, remember that carbons in these triple bonds have this trigonal planar geometry. So all three things that each of these carbons are bound to are in the same plane. And that's true for the carbons on either side of the double bond. So you'll always have 6 atoms. Right? If I ask you how many are in the same plane, if you got one double bond, there's going to be 6 atoms. Again, you're going to look at the carbon and everything the carbon that's in that double bond, everything that carbon's bound to, all lies in the same plane. Okay, so moving on to my next example here, again, I'm going to look at my carbon and all the 3 things that it's bound to are in the same plane. I'm going to hop over to the other side. It's also true for this carbon here. So these 2 methyl groups are not in the same plane. Everything else in orange there is. Okay. Now we got to do cis or trans designation. What about the molecule on the left? Is that cis or trans? Trans. They're pointed on opposite side. And what about on the molecule on the right? Cis. Now they're pointed on the same side. Okay. I guess we can look at alkynes and ask a similar geometry question at this point. Use a different representation here. I don't know a better way to word this, but which of these atoms, so similar to how with our double bonds we can ask which one of these atoms lie in the same plane, with our triple bonds we can ask which one of these atoms all lie in a line, right? We have that linear geometry for our triple bonds. Okay, and again, we're just going to look at the carbon in the triple bond, and it's the two things that that carbon is bound to. Jump to the other side, same idea. So for this one, it would be this one and this one. So all four of those atoms are sitting in a line in this structure. Everything else is lying somewhere, outside of that. So these are all doing their own thing. But those four atoms in orange are all sitting in this perfect line in that molecule. Okay. All right, so now I got to do some nomenclature here. So nomenclature is one of those things where if you got it down for the alkanes, all we're going to do is tweak things just a little bit here. Right? But if you're still struggling with the alkane stuff, then all of a sudden this is going to seem like it's just piling on, right? So it's one of those things that really builds, and we're just going to take this core concept and build and build and build. Our rules don't really change, but now we have this new functional group that we're going to have to identify in our molecule. Okay? So first, let me just give you an example. I'll do two. All right, actually the first thing I want you to do, take this and turn it into a bond line structure, right? I gave you this long drawn out Lewis structure. Make sure that you can turn it into a bond line structure. What's up?
Is that second hydrogen, or that second carbon supposed to have just one hydrogen, or no? Is this 5 bonds?
Yeah, totally. Yeah, good call. All right, should look something like that. Okay, so I'm gonna just give you the punchline here, and then we'll sort of try to pick it apart a little bit. This molecule's name would be 1-propene. Okay? Remember that if we just had a 3-carbon alkane, what would the name of this molecule be with all single bonds? Propane. Right, and if I wanted to do the bond line structure of that, it would just be a little TP thing. So now I have a double bond in there. First thing that you'll notice, so first of all, these were the alkanes. These are alkenes. So first thing note is that my ending has changed from ane to ene. Right, so the alkanes all had this ane ending going on. The alkenes are all going to have this ene ending going on, right? E-N-E. Okay? The other thing is I have to indicate the position, the position of this double bond. Okay? So unlike our alkanes, there wasn't any functional groups in there, so we didn't have to worry about where they were located. If there were substituents, we would number them. right? These alkenes, now we have to put the position of that functional group. So that's where that 1 comes from, indicating that it's between carbons 1 and 2. You always put it on the lower number. Okay? So if I had something like this, find my parent chain, my longest continuous set of carbons, 1, 2, 3, 4, 5. And since there's a double bond, it's pentene. All right, I still use that pent prefix because there are 5 of them, but now I have that different ending, that ene ending. And then I have to indicate the position of that double bond. That double bond is located on carbon 2, or between carbons 2 and 3. So I indicate its position with the 2. This is 2-pentene. Okay? When we go to alkynes, got that triple bond in there. 1, 2, 3, 4. Actually, let's do this. So again, take a second and convert this Lewis structure here, this structural formula is the fancy way to say it, into the bond line structures for this alkyne. All right, so I got 5 carbons, so kind of how you could think about it. You can do your normal 5 carbons, but you got to put that triple bond in, and you can't just do it like that, right? Because the triple bond has to look like it's this linear shape. So instead I'm going to stick it up here. So that would be the bond line structure of that molecule. And this one here, 5 carbons. So what's the prefix I'm going to use to indicate the number of carbons? Pent. So this would be pentyne. And again, I got to indicate the position of that triple bond. So the full name would be 1-pentyne because it's between carbons 1 and 2. Okay? So when we had our alkanes, we had the ane ending. Our alkenes have the ene ending. And because we have this functional group in there, we also have to indicate the position of the functional group. And then when we get to alkynes, they have this ine ending. And again, we have to indicate the position of that functional group. All right? Other than that, our nomenclature is, sort of stays the same in terms of if there's anything sticking off. So let's do a few examples here. We'll work with both the Lewis structures and the bond line structures here. We really want to be good at all these different representations, right? Being able to see that they're the same thing. All right, anybody got this first one?
2-butyne.
Nice. All right, so first of all, parent chain. 1, 2, 3, 4 carbons. So that's bute. It's got that triple bond in there, so I'm going to need to use the ine ending. I got to indicate the position of that triple bond. It's between carbons 2 and 3, so I'm going to pick the lower number, so this would be 2-butyne. All right, what's the next one? Anybody got that one?
2-hexene.
Nice, okay. So 1, 2, 3, 4, 5, 6 carbons in my parent chain. So hex. I've got that double bond, so it's going to get the ene ending, hexene. And then I got to indicate the position of that double bond, so in this one I'll number it both ways. Am I going to pick the red or the blue numbering scheme? Yeah, I want the lowest numbers possible in my name here. So I'm not going to make it 4-hexene. It's going to be 2-hexene. Okay. With our double bonds, there's actually one more thing that we need in order to fully make complete the name here. And that is that cis or trans stereochemistry, similar to like what we had to do with our cyclohexanes. Right? So would this 2-hexene be the cis or the trans 2-hexene? Are they located on the same side or opposite sides? These two carbons here. Actually, you can always look at the hydrogens too, but yes, these two carbons here are on opposite sides of that double bond. So this would be the trans 2-hexene. Take a second and draw me the cis 2-hexene.
Wait, I thought you said double bonds can't rotate.
Double bonds can't, what did I say?
Wouldn't if you have them wouldn't they be facing on the same side?
Totally, they're different molecules. So you're gonna draw me the cis version. It's not like this one will turn into the cis version. They're two separate molecules. They got their two separate properties. If I was going to do the cis version, I'm going to have to put those two groups on the same side of my double bond. So this would be the cis 2-hexene. And yeah, completely different molecules. Like if you go to like Sigma Aldridge or you go to your stockroom or something, you can find a bottle of the trans 2-hexene and a bottle of the cis 2-hexene, right? They're just two separate molecules. They have different properties. Okay. The one thing I'm going to do to complicate things here with the alkene and alkyne nomenclature is this is our first functional group, functional group outside of like the halogens, okay? And this is our first functional group that has what's called priority. So what the heck does that mean? That means that if I have, for example, something like this, okay? First of all, take a second to count the number of carbons that are in this molecule here. So you got 1, 2, 3, 4, 5 carbons in this molecule. So that's my parent chain is going to be the pentene. This right here, this substituent sticking off, what would we call that? What's our prefix for that? So this would be a fluoro group. Okay? But now when it comes to numbering this parent chain, we have to prioritize our functional group, prioritize the double bond. All right, so what the heck does that mean? That means I'm going to do it the long way. I'm going to go in and put in my two numbering schemes. Previously, we were picking whichever one had the lowest number in there, right? Which would be the blue one, because that would put the fluoro at carbon 1. But instead, we're going to prioritize, because we have this functional group in there, we're going to prioritize that double bond, meaning we're going to completely ignore the fluorine and pick whichever numbering scheme gives that double bond the lowest possible number. Okay? So we have to prioritize our functional group when we number. So in this case, it would actually be the red numbering scheme. So this would be 5 fluoro 2 pentene. All right, and then actually to complete it, what am I going to need to put out front? Trans. All right, so this is the one sort of tweaking of the rules with regard to numbering our parent chain. Now we have to, so special rule for our alkenes and alkynes. When numbering that parent chain, we got to prioritize the functional group, prioritize the double or the triple bond. Make sure that it gets the lowest number. Right? We always only have these two. Once we find our parent chain, we only have two possible numbering schemes. So you can always just put them both down. And in this case, when you have alkenes and alkynes, you're going to pick the one that puts the double bond or the triple bond at the lowest possible number, ignoring all the other substituents. Cool? All right, so again, today will be my first day that I'll have these in-person office hours. I have a class right after yours, so it'll start after that class. So what is that? So it's 9 to 10. So yeah, starting from 10 to 11. And it's like second floor of this building right next door, right? It's actually technically Science 2 still. Room 275, it is not my name on the door. It's some other person's name, but I'll be in there. I'll have the door open. We do not have class on Monday, so y'all enjoy your long-ass weekend. I'm pumped about it. All right, have a good one.